Hi everyone, welcome again. Today we'll be talking about Encrypt protocol, another privacy protocol on Solana. You can check them out on X here. I have encrypted capital markets, Encrypt XYZ. So they offer FHE on Solana. So we'll be dissecting FHE and the entire Encrypt tech, how it works on the surface level. Here we have FHE. What is FHE? FHE stands for fully homomorphic encryption. I didn't write that here, so you can just take that. Yeah, fully homomorphic encryption. What does it do? What does it mean? Now, encryption or cryptography, it's basically encrypting plain text, converting it from plain to ciphertext. And then if you need back the plain text, you decrypt the ciphertext to get your plain text back. Now, in concept of homomorphic encryption or FHE, is basically working and processing data that has been encrypted without decrypting it. So, as this illustration shows you, user has $100, you encrypt it with, let's say, encrypt protocol, is locked and is converted to a ciphertext. Now, that ciphertext bus is stored on chain in an account. Now, it's time to, let's say, increment the account or add to the user's balance. What the encrypt protocol, encrypt network does is that it doesn't decrypt this ciphertext to get back the $50 or $100 amount that was there initially. What it does is it works directly on this ciphertext. So, like I said here, the executor node computes the S50 blindly. So, if you're adding to or processing or analyzing or anything you're doing on ciphertext, basically, you won't decrypt it. The FHE just basically means working on ciphertext without decrypting it. So, just encrypted data, process, do everything on it without decrypting it. So, you can see the whole flow here. User encrypts money and then stored in the ciphertext box, goes on to the network computes, adds or does anything it wants to do, but yet doesn't decrypt. So the network does not know the content of that particular ciphertext. It just works on it and updates the ciphertext. That's basically what Encrypt does. That's what FHE does. Now, talking about FHE in context to Encrypt protocol, we have our regular traditional Solana account, which is this, where you can view the details, the balance, the status, remaining fields inside the account. You can fill them there. But there's a shift in paradigm with Encrypt. So Encrypt uses a ciphertext account. So this ciphertext account stores ciphertext of regular accounts with a status flag. We'll get to that. So this is just basically a shift in paradigm. You don't store plain text anymore. You store ciphertext on the blockchain. So when we need that text, we can decrypt it if the user wants to read the content of the text. But if the network wants to work on it, it doesn't need to decrypt, just work on them directly. Now, we have the network key and the user keys in the encrypt protocol. When you're encrypting your text, you need a public key, basically an encryption public key. And decrypting also requires a private key. But in this context, we have one public key for encrypt protocol. You pass that in the client. If you check out the client, you see where the public key is being passed in. They have one public key for the entire global encrypt network where everybody can pass it in the clients here. So everybody uses the same public key to encrypt their information. Now we have the fragmented private key, which is the private key for this public key, this pair. The private key is not, it's just one. So to keep it safe and to avoid tampering, it's being shared. So it's sharded amongst the crypto network. So they have an MPC network where we have the crypto nodes. We'll come to that, the use of the crypto nodes in the network. So the private key is kept amongst these shards in the network. And then, sorry, these nodes in the network in shards. So anytime there's need for decryption or there's need for data to be read, we would assemble this key back and then decrypt network. The decrypt network decrypts and sends out to users. Yeah, that's how basically this works. Now we'll talk about the core architecture, how it works. The flow, first of all, is basically the encryption is done locally. I forgot that. So first of all, encryption is done locally on the user's device via maybe the React SDK or the Encrypt SDK. Yeah, you can see that we have their code base. This is their docs, so we can check here. I'll show you code still. Yeah, we'll do that. We have the encryption done locally on the user machine, then proceed to the on-chain component where we have an encrypt DSL. This is what I mean by an encrypt DSL. So they have special creates and a special domain specific language you use to write. So they have their own logic. This DSL contains the encrypt function macro for graphs and a whole lot. So we have support for Pinocchio, native, and all. These are just the crates. So with these crates and our existing underlying Anchor clients, we can write Solana SVM, write Solana programs basically. So we have the business logic, which is written with your Anchor, and then the encrypt crates and the encrypt DSL. Then we have ciphertext accounts. Remember I said we're not storing in plain text accounts as usual, traditional Solana methods. We're using ciphertext accounts. Then we have the encrypt network, which consists of, we have the executor node, we have the decryptor node. So the executor nodes handle the complex mathematics, the whole computation, the FHA math, and then the decryptor nodes only decrypt ciphertext or decrypt information when needed by the user. So don't get me wrong, decryption is only necessary or is only needed when the user requests it. But by default, the network does not need decryption. It just does all FHA math. But if the user decides to request to see his data, remember data is encrypted first. If you want to see your data, like decrypt it, you have to request and use the decryptor nodes to get to that. So the event bridge here, I was just basically illustrating how this works basically. Now the flow of encrypt is this. First, you have an instruction. The instruction bears a graph in which you send or you state your computation needs or how you want your computation to be done, and this computation is routed to an executor node. So when this computation is done, I think code explains better. We have this. This is a coin flip program. We have this is search for an increment or the main game instruction. Yeah, this is the play instruction. I think this is the main instruction here. After the CPI to the encrypt program, we have where the graph is used. So this graph is where the off-chain computation happens. Remember, they are working on accounts without decrypting them. So this graph, I think it's linked to this. Yeah, this is a graph using the encrypt function macro. And this graph does computation. How do we sync back now? Because the flow is ciphertext accounts are created and the graph has to perform computation. The graph has to state computation, the network performs it and then updates the ciphertext account. So as usual, the regular Solana way, we can emit events. So an event is emitted, the off-chain executor catches it and does all the computation and updates the blockchain. So there are two transactions. First, your regular transaction, which is this, that creates the account first. Then a second transaction that follows after the graph has finished computation and updates ciphertext. So we'll come to that here. Talk about data ingestion, creating state, how it basically works. Like I said initially, the ciphertext account. This is it. I think it's a 98 bytes account with 2 bytes discriminator. All this you can see here. Yes. So you can see here, we have a ciphertext digest. We have the authorized, which writes in who can view this. Yeah. We have the network encryption key. I talked about that. We have the FHE type. We'll come to that. Basically, let's talk about it before. So we have FHE data types. I missed that here. So ease encryption on the FHE network, we have FHE types that work in the network. We have what we call encrypted data types. You can see more of them here. So instead of using your regular U64, we have EINT64, we have we have encrypted Boolean. There are many more. You can check, you can see a whole lot of them. Boolean vectors, arithmetic vectors. If you need plain text types too, we have types for that. We have vectors. You will talk about, okay, no, I think that's where it ended. So we have special data types for this purpose, FHE. And then routing back to where we were at. So we have a status pending. This status pending is very important, a very key component in ciphertext anatomy. Remember I said that first of all, when a transaction is or instruction is run, the ciphertext is created with a status of pending. Now, after it has been routed and performed on by the executor nodes, is bumped up to verified. So we'll talk about that and how that works. Then we have the seed conflict disaster. I came across this when I was reading the docs and building. So I was asking myself, now if you check the encrypt docs on ciphertext accounts, you see them tell you that ciphertext accounts are actually random key pairs, not PDAs. So you ask yourself, why then? Why did they not use PDAs? Why are we not using PDAs? Instead, why are we using random key pairs, regular key pair accounts? To avoid collision issues. Yeah. So if one user, another user is trying to use a PDA, I mean, it's quite difficult handling and storing and remembering all the seeds. One can decide to use another. User can be using another seed, another user can be using similar seed to cause collision and all. But with random key pairs, it's very difficult to actually generate what somebody has generated. Like, I don't think that is even possible. So you're safe with these random key pairs, and we can have random ciphertext accounts. Then we have the authorization. Remember, I said there's an authorized keyword. So if you decide to act on a ciphertext when you're not permitted, like, you actually get bounced back. Like, the transaction would fail because you don't have this, you don't have authority to the account. Then we have plain text initialization. This is mostly demonstrated in the program. If you see the program, if you're working on, let's say, a counter program like I used before I made this illustration, so you don't necessarily have to encrypt every time. The encrypt program can encrypt for you. We would handle this when we write code. When we write code, we'll see how that works. So the smart contract can just do the encryption for you, basically. Yeah. So you can just push a raw data, and then the encrypt program wraps and returns locked ciphertext. Yeah. Now we have the computation graph. I think this is the complex part of it. Yeah. So remember I said there's a graph. So the graph is the very important component that links our transactions to the executor nodes. Basically, the FHE computation is being described like by the graph. So maybe you're doing a counter program where you have 10 plus 1. You define your code in a graph like I showed you here. That's what the graphs look like. This is a graph for a coin flip. You can check another. This is a graph for increments, decrements. Graphs can get more complex. Let's see a swap account. Anything in Pinocchio. Let's look for the graph for this. You can see an add liquidity graph. So the graphs can, it's just, the graph is basically computation. That computation you run there, since we cannot compute on the accounts because they are encrypted, just define the computation and pass it to the executor node. That's what the graph does. So this is basically the duplicator constants. Read about them here. So there are plain text values that are embedded directly into the computation graph when necessary. Then we have the two transaction computation loop. Like I initially described, when you execute first, the smart contract flags. You know why I use smart contract here? The program, rather. The program flags ciphertext as pending locked. That's the first step. Then, after a while, the executor nodes perform transactions, then update the state. Then the ciphertext is switched to verified here. So this changes from pending to verified. That's what happens here. Yeah. So that's the loop basically. This would be more explanatory or better described when we get into coding aspect. This is just an introductory video to the encrypt hole. So we've spoken about the transaction flow. Now coming to decryption, what are we decrypting? Like I initially explained, the user might need to decrypt his or her data. You have a balance of $100. You encrypt first and perform computation. Money rolls in $50, $100, $10, and whole lots. And all those computations are done. Now you want to see the balance of your states on chain, your balance now. You cannot access it directly. You have to decrypt that ciphertext that the FHA network has been updating and working on. So this is basically the flow. To decrypt your data, you have to call an instruction, a transaction, a request decryption transaction. You can see here. This is a sample. So you request value decryption. The reason why it is a transaction is that the decryption key, remember, private key is held by the MPC network, the decryptor node. So you request a transaction, the program verifies that you're actually authorized to decrypt and view this information, the whole consensus and all. Then we request a transaction and it's routed to the decryptor nodes where they process, decrypt, and you have to poll with your front end. You see that you check the client's code, you see the polling parts. So you poll and then you can view it. I will just show you so it's easier for you to understand this. Okay, you see here, so you request decryption. So you send it decryption transaction, then we wait for the executor to decrypt it. After decrypting it, we pull until it's decrypted, then we can do what we want with the value, basically. So now this request digest receipt, this code check, is basically talking about how they confirm that if there are two transactions, basically, how do we confirm, since the Solana chain cannot wait, how do we confirm that this person requesting decryption is actually the right person that is supposed to view this data? Or is actually if you request decryption, how am I sure that this text is actually the correct plain text? So first of all, there's a pending digest, basically. The hash get a digest, and this digest is used to confirm. So when you query the decryptor node, the decryptor network for your data, is a digest that is stored first locally on your system, and then this digest is used to confirm the incoming data. And that data, when you get your data, you can either do two things with it. Now let's assume we've gotten our data. You can either decide to use it in memory or save it, let's say, to a public Solana account. That is like the review part. Remember, this data is encrypted, so after decrypting, you can decide to use it in memory. I'm looking for code on that. We have I waste our time looking for proper code on how that. But just know that when you get data after decryption, you can either use it in memory, they use it to perform your swap or anything, or decide to save it to an account. Let's assume it's a game and they play. You can It's a game of be a coin flip, as they've said here. So to review the final amount, after, remember the moves are encrypted and all. To review the final amount of the result, you can try to write to the game struct, which is this permanent review, the second part, or you can try to use the last state in memory to do that verification and continue further logic on it. Yeah. Now I've already explained the spoof prevention, like preventing spoofing. It's basically having the ticket stop. That's just the pending digest, and then forgive me for using smart contract everywhere. I was just that's supposed to be programs, please. Program does the callback and all. Yeah, so I'll just talk about the entire flow with a diagram. I have a diagram of the entire flow here. Let's look at the full flow of using an encrypt protocol. So we have plain text of 50, let's say a game or user account. Then it's encrypted locally. Now look at this. We have the client layer, which is off-chain, your layer. We have the SVM layer, which is Solana blockchain, and we have the encrypt protocol layer, which is their off-chain node network. We have the client app with plain text of 50. First of all, you encrypt using the SDK. If I show you, I can show you that here. Um, this is there's an encrypt. Oh my goodness. I'm going to go to see that in better. So you encrypt locally. You After encrypting locally, an account is encrypted on the Solana blockchain. That is ciphertext account holding your value. But remember, is has been encrypted. So now you want to, let's say, add 10 to this 50 existing on this account. So you construct your instruction that triggers a graph. Execute graph instruction I've showed you in other examples. When you execute this graph instruction, it's change your status is now pending, meaning that nobody can actually request. Everybody will have to wait till computation is done before you act on this account. So status is now pending, and the network moves computation to the off-chain node. So the off-chain nodes work on ciphertext, computing and adding 10 without blindly seeing computing and working on this 50 without knowing the value. They don't know it's 50, just a ciphertext, computing 10 on it. Then this result is submitted back to the chain, comes back to the chain, and the status is verified. So moves from pending to verified. Now your ciphertext or your account holds 60, still a ciphertext though. Now you want to view your balance, you use your client as the TypeScript client to which waits till this whole process is done. And you request decryption with another transaction, then the pending digest is logged and the ciphertext is being decrypted. Once it's decrypted, this is not, hold on. Yeah, this is being decrypted. Then an event is sent to the decryptor nodes. They do the whole merging of the private key to reveal the content of this. They do the whole merging of the private key to be able to decrypt from all the nodes. Then they decrypt and they have this. Then you can decide to either, you can see it here. You can decide to either use it in memory or maybe save it to a PDA or an existing account. So it's just basically an introduction to Encrypt protocol. We might have a code session where we would write code on maybe a simple program, a counter program, a coin flip, an escrow, anything simple to just test and see how FHE works on Encrypt. Yeah, so see you in the next video.